So we have Professor Dmitri Efetov again for lecture today. Please welcome Professor Efetov. Yeah.
Okay. Okay. Thanks a lot. So today I'll continue sort of the discussion with some more up-to-date developments. And the first thing I want to talk about is just sort of addressing sort of a ongoing improvement in the quality of devices. And just what I want to highlight is that throughout sort of the field, as the field developed, actually we noticed a lot of sample-to-sample variations, where in particular, very early on in the field, so in the first 1 or 2 years, different devices often showed quite different phase diagrams, even though the twist angle was sort of very similar. And here is just some outtake of our one of our earlier papers that we published in 2020, which basically shows several devices with several sort of twist angles, but also with several dielectric thicknesses of the HBN beneath it. And so basically, I just want to show this to motivate that really throughout the years, it was clear that the phase diagrams seem to be somewhat sample dependent, and microscopic sample details such as, for example, dielectric environment, such as twist angle disorder, strain, can influence the correlated phases. So basically, one of the sources of disorder in the systems, as we know now, is twist angle disorder. And in particular, twist angle disorder can, of course, also induce some strain into the system. And basically, just what is twist angle disorder? So, for example, this is like a map of a local twist angle that has been performed by the group of Eli Zeldov on one of our devices. So they were basically extracting the twist angle and the position of the sort of band insulator densities along a line like this over the device, which basically scales over a period of something like 20 micrometers. And you can see really in the device, the twist angle can vary quite a bit, right? So not too dramatically, I have to say this is not even a bad device, but over like a length scale of 10 micrometers, it can sort of vary substantially. Okay, and for example, also this is some data from the group of Ali Yazdani, where they, of course, in STM, they can actually measure the environment around sort of the probed area, and they can estimate sort of the strain variation there. And they also found that, for example, in devices with 0.2 interlayer strain or 0.03, almost strain-free devices, there were quite some differences in the spectra. For example, the charge neutrality point in strain devices usually was absent. However, in some of the most homogeneous strain-free devices, they saw a gap also developing at charge neutrality. So I think to summarize this a little bit, indeed, sort of the phase diagram of twisted graphene seems to be dependent on the details of the devices, and in particular, something like strain can tip the balance of the ground states a little bit in one or the other direction. So, and basically, I think if you look at literature from local probe studies, again, mainly performed by the STM groups like Ali Yazdani or Stefan Nashbergi, in the typical strain devices, what one typically observes is that the filling factor 0 is not gapped, and filling factor ±2 exhibits IKS order, which has been resolved in sort of breaking of the symmetries on the graphene lattice. And for example, in ultra low strain samples, filling factor 0 is usually gapped. and filling factor ±2 could be potentially a TIVC state. So, okay, so there are like really minute differences based on this sort of strain built-in. And so basically, to address this issue, so basically my group has been in the last years trying to sort of improve the device quality. So some of the ingredients that we have been implementing is, for example, deterministic edge clamping that basically helps stabilize the general twist angle. So basically the idea is that when you sort of assemble the device, you try to clamp the two edges of the graphene layers to HBN flake. And with this, you can sort of stabilize the twist angle and make sure that it doesn't basically fall back to 0 degrees in the fabrication process. And the other thing which we also were sort of experimenting with is active bubble removal protocol. So again, in these assembly of two-dimensional materials, what happens often is that some bubbles can be trapped between the layers. And of course, these bubbles basically are due to sort of the collimation process, which can trap some air, but also some impurities between the layers can sort of move around and localize in certain areas. And of course, these bubbles are heavy strain centers, and around these bubbles, really strain is quite pronounced. So, for example, we improved sort of this bubble-free assembly by sort of playing with the temperature in the assembly process, which really helped to remove many of the bubbles in the active device region. And so with this, we kind of thought we stabilized the process quite a bit. So in some occasions, we had really macroscopic tens of micrometer scale devices that showed a very homogeneous twist angle among sort of the device area. And overall, I think in sort of applying these improvements, which again, we published also in this paper here, the details of the fabrication protocol, we found that something like 40% of all the devices showed a magic angle in some areas of the device, and about 20% of the devices show superconductivity in them. Okay, and so in principle, we're quite happy with this, but of course, we wanted to further improve this. And so right now, what we're really investing heavily in our group is really a deterministic imaging of the moire during the fabrication process, and also after the fabrication process has been done, already in sort of fabricated moire devices. And here, two sort of imaging techniques which we sort of employ in our fabrication processes right now is, for example, torsion force microscopy. It's kind of a technique which is also used, for example, by David Hubbard-Gordon's group extensively, which sort of this paper is from them. And it really allows quite well to image the moire superpotential in open surface devices, so before encapsulation. And here you can see really one can really resolve like on a several micrometer scale quite nicely the moire. And also in this case particular, which is highlighted here, one can also resolve the super moire, which comes from the potential alignment also of HBN underneath it. However, of course, there's still like some uncertainty because when we make transport devices, we still need to encapsulate such an open surface device so things can still move around. So what we are doing right now, we incorporated a scanning microwave impedance microscopy technique to our clean room, where basically, which allows us to image the moire also after the full encapsulation of the devices. So you can actually image through the top layer of the HBN. If it's not too thick, it sort of shouldn't be too thick. Then the sort of imaging sort of is quenched. But if it's something at this point, it's 3 to 5 nanometers thick, you can actually image the moire through the HBN with this technique. And basically, the idea is then, of course, to sort of have really first of all, a production of ultra-homogeneous TBG devices. Because of this technique, you can position your device exactly where you find the most homogeneous area. And second of all, you can also, of course, then produce transport devices which have well-defined strain profiles. So, of course, hello, sorry, can you still hear me?
Now we can.
Yeah.
Somehow, sorry, somehow my speakers turned off. So sorry, 1 second.
Yeah, we can hear you now. It's working now.
Okay, now my speakers are back. Sorry, somehow my speakers just turned off. Okay, sorry about that. Okay, so then I just continue, right? And so basically the idea is, of course, now to sort of know exactly in the transport devices what does really the moire look like, what does the sort of strain profiles look like, and to sort of A, increase the yield of the so fabricated devices, but then B, also to have much better information of what's sort of the ingredients, the strain, for example, that that we are probing. Okay, so with this, sort of this is one of the developments. So the other development which we sort of undertook before we sort of before we are getting into sort of the next generation of devices, we also went back to sort of our catalog of devices that we have measured over the years. Of course, as I said, there is quite a bit of variation between all the different phases, but we thought it's really worthwhile to just analyze them and really build a statistical phase diagram out of all the different devices which we have already fabricated to really convince ourselves what are the most robust, most recurring phases that we can have. And we fabricated over the years probably something like 50 devices, but then we found at least 20 devices which we had a complete data set, basically magnitude transport, Hall effect, and temperature dependencies and some things like this. So complete data sets of them. And I asked my student really just to analyze and assemble cumulative phase diagram of them. And here is, for example, just to give you an idea, here's, for example, on the left side, just a bunch of different devices, and where we basically, with a Arrhenius fit, we basically try to identify deterministically areas which have, sorry, mates. Okay, yeah, which have basically insulating behavior, and where we can actually extract an energy gap from the Arrhenius fit. So all those regions are seen here. And then we can basically also accumulate them into a phase diagram, which basically gives you an overview of the gaps of all the different devices. And we can also, from this, we can then build a histogram of what type of phases are sort of observed in most sort of reproducibly in all of these devices. And what you can see here, for example, is sort of the occurrence between sort of the insulating gaps, basically the insulating states at integer filling, which form gaps. And you can see, so basically the gaps that are most sort of recurring are the gaps at plus and minus 2. So these gaps are basically in 3/4, so 75% of the devices basically are present there. So they're extremely robust. We observe them really in most of our devices. Then the filling factor free gap is also quite often there. However, we basically never see gaps at 1, -1, and -3. However, at -1 and 1, we still see some resistive peaks, which again hint to some sort of MOT-like phase, but they are definitely not developing gaps. Okay, and last but not least, also at charge neutrality point, as pointed out before from the STM data, at charge neutrality point, we occasionally were seeing in two devices gaps occurring, but most of the time these gaps were not present. And in principle, of course, this is an interpretation, but in principle, it supports also the understanding that strain is something which can sort of remove the gap at filling factor 0. And you need to get very, very sort of clean and homogeneous to get a sort of gap at charge neutrality point. Okay, so the other thing that we did, so with having sort of this in mind, and this is work which is, by the way, this is work which is still ongoing, but we hope to sort of wrap up the cumulative phase diagram paper in a couple of weeks. But the other thing which we were able then to do from this is we can also then trace back the devices which seem to have the most recurring features, where we really can compare this phase diagram one-to-one to sort of the cumulative phase diagram that we are sort of assembling. And this is sort of this device which I showed you yesterday. This is the device which really has all of those characteristics that seem to be very recurring. And basically, this shows you the resistance versus temperature versus filling factor. And really, what you can see is that here in such a phase diagram, you have a very well developed -2, +2, +3 correlated insulators with gaps below 5 Kelvin. Then we have sort of these superconducting regions, which are usually the strongest here at filling factor -2 to -3. So usually here we observe a strong superconductor with a superconductivity up to 3 Kelvin. However, other superconductors across the region are much, much more rare. So basically this superconducting region here that is highlighted here is observed in something like 80% of the devices. The other superconducting regions anywhere in other fillings are much rarer and usually also had a much lower superconducting transition temperatures. So, and then of course, above the superconducting state, we observe this linear and T strange metal phase. We observe Pomeranchuk effect. And then in general, closer to a filling to the band edges and to charge neutrality point, usually we observe something which is reminiscent of a Fermi liquid behavior. Okay, so then the other thing we were doing on this phase diagram, we could also really calculate or extract from this data the local power law exponent. So basically, we would just take a phase diagram like that, and we would fit it to this power law formula, where we assume the resistance could scale as something like a residual resistance plus some sort of power law temperature dependent resistivity. And we could then locally extract this sort of gamma coefficient here, which is basically just the power law of the temperature dependent resistivity. And replotting this graph kind of by extracting just the power law, you can see here on the right hand side is basically extracting the power law, where the regions which you see sort of in a reddish yellowish are kind of the regions which have a power law of around 2. And the regions that you see here in purple are the regions where the power law of the resistivity is right around 1. And so basically, I think you can already see that close to charge neutrality point here, there is really like a wider region that scales closer to a power law of 2. And then you see at sort of, especially there are really large regions here in this phase diagram, which scale rather linearly and have a temperature dependence, which is really closest to a linear temperature behavior. Okay, so now sort of the other thing which we noticed when you started plotting things this way is that really, as you can see here, around filling factor 2, first of all, there's a strong asymmetry between sort of the electron and hole dopings. And in particular, you can see here between -2 and -3, there are really these dome-shaped regions here with a sort of onset temperature of around 10 Kelvin. They're they're extremely reproducible over all of the devices that we were plotting, and also on the electron side between 2 and 3, also these regions appear. And of course, when we looked at them, you know, you could mistake them very easily for superconducting regions. But I will, in a second, talk more talk more about them, what we think currently, what these features are. Okay, so but a long story short, so basically, I think from this type of phases that we could sort of produce, looking at all of different devices, this is something which we believe is the most sort of reproducible phase diagram, where you can clearly see that what we can work out is that really the integer fillings such as 2, 3, and -2 are typically gapped. The filling factors 1, -1, -3 are typically not gapped and are metallic, or maybe have some sort of weak sort of a temperature dependence, like the Pomeranchuk effect. And then really close to around charge neutrality, we believe it's reminiscent of a Fermi liquid behavior. And then really a new feature, which I'll discuss in a second, where we believe sort of on the hole filling side of -2, but also on +2, on the electron filling side, they're really large sort of metallic dome regions, which are in most cases just metallic. And then this metallic region turns superconducting in most cases just for a portion of this region, just mostly close to the charge to the filling factor -2. Okay, and so in the next sort of couple of slides, I just really wanted to talk specifically about this region here, and also tie it up a little bit with the previous measurements that has been in particular performed in STM experiments. And basically, the story is the following, that the groups of Ali Yazdani and Stefan Nashbergi, they have been actually investigating the gaps around the around the filling factor -2 quite extensively. So whereas the group of Ali Yazdani was focused on magic angle twisted bilayer graphene, the group of Stefan Nashbergi was predominantly looking at magic angle twisted trilayer graphene. What I have seen is that really they observe a correlated insulator gap around filling factor -2, and then slightly shifted from this -2 region, basically most closely to 2, but really extending also almost to a filling factor -3. They also observed some sort of R3 pattern, which really existed just in this particular region. And this R3 pattern basically was highlighted by having these sort of enhanced or enlargement, 3 times enlargement of the unit cell on the graphene, which they can really follow and trace basically depending on the filling that they were applying to the system. And here, as you can see in this data here, this sort of R3 pattern was really peaking around filling factor -2, a little bit closer on the whole side. So this gap was interpreted as some IVC gap that was forming in the system. Again, similar sort of results were obtained in trilayer graphene by the Nashbergi group. And so basically, it sort of seems to be implying, in my opinion, that this sort of gap here could be really be sort of reminiscent of some sort of IVC order building up around -2. So the other sort of development over the last year or so was also that within sort of this larger gap region, again, which we could interpret as an IVC gap, also superconducting regions have been found. Okay, and this is data again by Stefan Nashbergi groups on trilayer graphene, but also in sort of transport tunneling devices by the group of Pablo Herrero. They also observed basically a double peak structure where one of the peaks was kind of attributed not to superconductivity, but the other sort of a smaller gap was attributed to superconductivity. So both basically studies see two types of gaps, right? One potentially an IVC gap, the other one a superconducting gap. And in principle, these gaps coincide in a certain region of doping, but then they kind of also diverge from one another. So the superconducting gap typically lives much closer to filling factor 2, whereas the IVC gap extends much further out to filling factor -3. So, and basically now coming back to transport, now that we really have very strong evidence on sort of investigating a similar region in the phase diagram from the transport, what we were able to do is really map out these regions in our transport maps and really look in much more detail how sort of the temperature dependent transport and also how the temperature dependent Hall effect evolve across this phase diagram. And so basically here on the left hand side you can see this phase diagram here. So you can see here filling factor -2. Left of it, you can see the superconducting region where resistivity really drops to 0. And then you can really see this larger sort of dome-shaped region where resistivity actually does not drop to 0. And by, of course, we can also apply a control experiment, but just applying a small perpendicular magnetic field, we can completely kill the superconductivity here. And then basically end up with only the sort of second. Okay, so then you can see here sort of the line cuts that I'm presenting here. So this is R versus T on the top, and on the bottom you can see also the Hall effect versus T. So basically, it seems to be that there is really a coming sort of, if we take temperature-dependent resistivity cuts over this region, we can see that really there seems to be two types of transitions. So one type of, at high temperatures, we're basically in the symmetric state, which is identified by this linear T resistivity. Then we have sort of at around 6 or 7 Kelvin, we have a broad transition to a sort of much less resistive state where the resistance really drops from something like 10 kilo ohms to just a few hundreds of ohms. And then eventually the system drops to superconductivity where it is basically at zero resistivity. However, again, if we apply just a magnetic field just in this region, we can completely sort of kill the zero resistivity to some sort of a higher value, but this larger transition is really not changed in the process. So we believe that this larger phase transition here is not directly related to superconductivity, but we believe it's rather related to this IVC order that is setting in. And below that, at much lower temperatures, out of the IVC order, then the superconducting phase nucleates. So the other thing which we sort of can tie to this sort of to this thinking is that we at the same time also can measure Hall effect. And so basically, as you can see, sort of this dashed line here is the Hall effect. When we sort of look at the temperature dependence of the Hall effect in the symmetric state, it is sort of basically almost constant. And really at the same temperature scale as the IVC order sets in, the Hall effect really increases by almost an order of magnitude, which basically could mean that really there is some sort of renormalization of the Fermi surface happening, and really we are basically evolving into a smaller Fermi surface in this process. Okay, so basically, and this is all of this is basically also seen here in this phase diagram where we look at the Hall effect that transitions over here. So, so to summarize, basically we we sort of believe that really this type of IVC order is also seen in transport, where we can really also in transport, by pairing up temperature-dependent transport and Hall effect, we can work out these sort of IVC orders setting in. And also similar to sort of the two-gapped structures that have been observed again in the tunneling experiments. Also here we seem to have two type of distinct dome shapes. One related to sort of IVC ordering and sort of a metallic transition, and the other one which is also directly related to the superconducting phase. And to then also make the connection of why we believe the sort of dropping of resistance by the onset of the IVC order makes good sense, is that really, if you sort of look also at some theories that have been developed recently here by the Tim Wehling group, for example, and Rosaire Valenti, basically when the system orders, a lot of the fluctuating moments that are basically quite active at higher temperatures, when the system orders, these fluctuations are then stabilized, and therefore the resistance basically drops by an order of magnitude. And this is basically can be also just basically explained by having some sort of a bed metal behavior at elevated temperatures, where we have a lot of fluctuating moments, which is then sort of frozen out, and we sort of develop a transition into a good metal. And basically, all of this is basically, we believe, is seen here, where we again transition from a bed metal behavior, which is linear in temperature, where then the when the IVC order sets in, the resistivity drops by almost an order of magnitude, and out of this order, then a smaller superconducting phase is developing. Okay, so with this, I covered sort of the ongoing sort of investigation of the phase diagram of twisted bilayer graphene. I have to say this is all work in progress, so I'll be happy to also receive some comments about it. And other than that, I also want to kind of switch over now to sort of a different topic, which is the quantum twisted microscopy, which also we have been developing recently in our group. And basically, this development ties also a little bit into my original motivation, that we were throughout the years looking for fabrication protocols which would be a little bit more systematic and would give us a little bit higher throughput in assembling the phase diagrams. And here, this new technique, which was implemented by the group of Shahal Alani and Weitzman, caught our attention, where basically he presented a technique which basically allowed to bridge sort of between sort of a very fast assembly with a dynamical control of the twist angle of the device. And it was allowed also to perform local probe measurements similar to STM through tunneling measurements. And at the same time, it also gave some sort of momentum resolve spectroscopy similar to ARPAS. And it allowed basically to directly assemble the device and probe it at the very same time. And so this technique, unlike sort of ARPAS, for example, it's quite compatible also with millikelvin temperatures and high magnetic fields. It allows ultra high energy resolution because it relies on electronic tunneling, coherent electronic tunneling. It really is limited just by the quality of the interface, which we know in HBN graphene heterostructures is quite good. And it's only limited then also by the sort of electronic setup and the fridge temperatures. Okay, so and basically how this technique works. So this is a video from Shahal Alani's group. The technique works just by separating the two surfaces that you are sort of wanting to rotate with respect to one another. So in the case of twisted bilayer graphene, you can just put one graphene layer on this AFM tip, which is mechanically separated from the bottom substrate. Then you can assemble the bottom substrate on a rotatable platform, and you can basically bring them in touch with one another at locations which you like. You can rotate it and prepare sort of the twist angle dynamically which you like. And then basically, as I will show in a second, if you perform tunneling spectroscopy over interfaces that you prepare this way, you can also basically have ARPAS-like properties, meaning that you can translate the twist angle into momentum resolution, and also you can get spatial resolution of these devices, again, comparable to STM. Okay, so again, motivated by Shahal Alani's group, we also started doing this business. So first of all, we incorporated a room temperature setup. As you can see here, this is a room temperature setup that was just rebuilding a commercial AFM system, but really incorporating all the different ingredients that we need here. As you can see here, this is a typical QTM tip that we employed. So right now we employing also piezo-resistive tips that are basically self-sensing, where you don't need a laser beam to actually extract its deflection point. On these tips, we then deposit these pyramids with FIB, but also other techniques are possible to slightly create sort of this plateau-like elevated region. And then we just coat these regions with graphene, and we basically just connect them to the electrodes, which are also on the tip here. And so you can see here, so a typical SEM image of such a device, which basically shows a tip with a relatively flat region, which is just covered with a tent of graphene. And so this tent of graphene, you can actually image it with AFM, so you can actually go ahead and perform AFM images of your tip. And you can really convince yourself that the engaged region is A, it's flat, and B, it's kind of also of the right size that you need. So typically we use sizes of something like 200 nanometers. Okay, so this being said, so this was our first room temperature setup, but currently we also progressed quite far in building a dilution refrigerator setup, which performs at 10 millikelvin temperatures and has a vector magnet, a 911 vector magnet in it, which basically will allow us to really access the regime of these strongly correlated phases and superconductivity and twisted biolographene. And also furthermore, it gives us really the control of a magnetic field to probe sort of in parallel and in perpendicular magnetic fields the devices. And long story short, so here is, for example, some of the first scans which we implemented in this home-built QTM insert. So we basically can use these self-sensing tips actually to sort of resolve micrometer-sized structures on the devices. And hopefully in a few weeks, I will be able to show also some QTM data coming from the setup. Okay, so then just a little bit more details of the measurement scheme. So again, this is sort of the assembly, but then what's important is also to know exactly what is the van der Waals intersection, cross-section of the experiment. So basically, our tip is basically coated here with the graphene, which is sitting typically on some cushion layer of HBN and graphite. And we can apply just a bias voltage to this tip through sort of a voltage source. And then the device side or the sample side is usually some graphene layer, either single layer graphene or multi-layer graphene layer, which sits on the substrate, also on HBN, and which is sort of covered with a very thin HBN dielectric, which is typically 1 to 3 layers. That allows us direct tunneling from the top layer into the bottom layer through the HBN layer. And so what's important here is that if we now want to understand sort of the tunneling process, we really need to translate the applied bias voltage into some sort of energy profile across the tunneling interface. And sort of all electrostatic simulations show that really if you apply a bias voltage between the sample and the tip across the HBN layer, roughly to a third, I mean, we have again, we have extensive theory in the supplementary information of this paper. But basically, roughly to a third, this bias voltage goes into the shifting of the Fermi level in the sample. It goes roughly to a third to the shifting of the Fermi level in the tip, and roughly to a third into sort of the electrostatic energy, which is stored in the across the HBN layer. So okay, so basically by applying bias voltage, we shift the Fermi energies effectively of the two layers and allow sort of basically tunneling between energy and momentum matched conditions here. And the second really important ingredient here is, of course, the momentum cross-section between such a tunneling process, because we are not dealing with two Dirac cones which are sitting directly on top of one another, but we actually rotate them by sort of twisting the orientation of the top and bottom layer. But we really induce some sort of K-space mismatch between the two Fermi surfaces. And for small angles, this momentum mismatch is basically proportional to the twist angle itself. And so basically by twisting rotating these layers with one another, we're sort of changing the momentum between the two layers. So the momentum resolved tunneling processes, of course, change according to this twist. And this is what gives then the momentum resolution of the process. So here is so typical tunneling spectra as a function, again, of the bias voltage, which again, you can think of the bias voltage as being proportional to the Fermi energy, and the twist angle theta, which you can think of being proportional to the momentum. So basically, in some sense, this is really spectral functions, similar to what you observe, what you can observe in ARPAS experiments, that allow us that sort of encode within itself the information about the band structure of the material under probe. So okay, so basically this is typical IV data on the left side. In the middle, this is sort of conductance, nonlinear conductance measurements, and on the right-hand side, often we like to take the second derivative or the first derivative of the conductance spectra to reveal a few sort of features in much more detail that we can otherwise. Okay, so and basically this type of data is very characteristic of single layer to single layer graphene tunneling, and those features one can really explain as just basically mapping the momentum and energy resolved transitions that are sort of allowing for tunneling electrons to find sort of holes on the other side in which they tunnel. And basically, the two features that we're seeing here can be sort of understood by two main processes. So the first process is the onset condition. And the onset condition, as you can see here, this was worked out again by the first paper of Shah-Lalani, is a condition where basically the top and bottom layer, the Fermi energies are kind of exactly of the same value. And at the same time, also, you find exactly the same K momentum vector that the electrons can tunnel into. So this condition gives not a very strong tunneling current, and it basically is dependent mainly on the potential electrostatic potential within the dielectric layer. And this shows up in our phase diagram as these linear lines, and you can see them clearly here also in our data appearing, and they're really these onset conditions. And the second sort of much more pronounced and much stronger tunneling feature are these nesting conditions. And those are conditions where it's not just like one position of momentum that is sort of matching, but it's really like a longer sort of period over the momentum space that allows tunneling through in the process. And this is really the condition where the top and bottom layer kind of align, and the two bands, in particular the Dirac bands that are linear and which run for a long time, for a long period in momentum space, directly parallel to one another, this allows for really a lot of sort of these momentum and energy resolved conditions, and this resolves basically in these hourglass-shaped features, which are basically mainly dependent on the electrostatic potential here. And of course, here in the data, you see these features to be very pronounced hourglass-shaped features. Okay, so having sort of this capability to sort of really resolve these different energy and matching conditions between single layer and bilayer, single layer and single layer graphene, one can of course spin it further by using a single layer graphene tip to also of course tunnel into multi-layers of graphene. And so these maps that you can see here are basically the different measurements that we were performing on sorry, my screen froze for a second, but should be back, I think, right?
Yes. Yeah, we have been
yeah.
your screen.
Right. Sorry, 1 second. It's actually on my side. I stopped seeing my screen actually. Surprisingly, yeah. Let's see if I can bring it back. Jesus. Okay, now it's back. Sorry about it. Now it's all good, right?
Yeah, it's all good now.
Okay, sorry about it. Okay. And so basically here you can see that really this principle of analyzing these onset and nesting conditions can be translated more generally into also probing multi-layers. So those are again tunneling measurements into bilayer, trilayer, tetralayer, and pentalayer graphene. In this case, it's all AB stacking, not rhombohedral stacking. But as you can see, so also here we can get really a more complicated spectra. However, we can trace them all back to the underlying band structure. And so we're right now sort of trying to see how far we can get it, the resolution here, and whether we can actually also extract hopping parameters quite accurately from these measurements. And we can really, in the process of understanding all those features that we are observing here. That being said, so this was AB graphene, but also we are now making our first attempts on ABC, rhombohedral graphene, from the QTM measurements. So basically what you can see here is on the bottom, you can see our first attempts in measuring ABC trilayer graphene. And the spectrum really, which we observe here, is quite distinct from the spectrum that we observe in ABA trilayer. And currently we're again modeling this and trying to understand all those features between them, with the hope, of course, to actually soon be able to also really image with the QTM rhombohedral graphene phases, also rhombohedral graphene aligned to HBN and things like this. And as you see, sort of the even at room temperature here, this is data that was taken at room temperature. We can resolve a lot of the features which with quite good resolution. Okay, so more to follow, I think, hopefully this year. Okay, so one of the things that we now also observed in just imaging single layer to single layer graphene tunneling was a little bit unexpected, where we actually at quite elevated bias voltages, we also have observed a splitting of the nesting condition into two peaks, which first of all was very surprising to us, because as you may remember, I made a point that the nesting condition was really originating from the slope of the two Dirac cones that were running in parallel with one another. And basically, as you would expect, for a perfectly linear band dispersion, you would keep this condition and you would expect only one nesting condition. However, very clearly and very reproducibly over like 20 devices, we see a splitting, and you can see the splitting is also quite characteristic, whereas we basically have an upper branch which sort of splits in from a bottom branch and then gets stronger and stronger. And so we were scratching our head a little bit about it, but basically we sort of concluded that really the most likely explanation is that maybe really some of the linearity that we assumed, or the perfect linearity of the drug cones that we assumed is maybe not exact and maybe more of an approximation. And if you sort of do this thought experiment by assuming a small nonlinearity in the spectrum, you would immediately find that naturally you get this type of splitting in the nesting condition. And this is here shown on the cartoon on the right-hand side. So if you just would assume a small nonlinearity in the nesting condition, you would see that instead of like having a continuous nesting condition that is just very, very fixed, has one value, you would actually develop these type of kissing points where really you would develop exactly two nesting condition depending on the the voltage that you apply to the sample, and some small nonlinearity would naturally give you this type of splitting in the nesting condition. So here we scratched our head a little bit where this condition could come from, but really the main point here is that a nonlinearity in principle could produce such a feature. Okay, and so basically when we were thinking about potential sources of nonlinearity with our theory colleagues from the Bernadette group, in particular Jonah was helping us to sort of analyze this. We started modeling all the different scenarios, and the first scenario was really just try to see whether a nearest neighbor hopping model for the graphene band structure would produce us some of these signatures, because as you know, the graphene band structure is only linear very close to the K point, but at elevated energies, it already develops some sort of nonlinearities, right? So the question was whether this nonlinearity at higher energies could be the one which we're seeing. And actually, we found that this cannot explain the features, because we would expect this nonlinearity to set in at much, much higher voltages than what we are probing. So basically, we were a factor of 5 off in the voltages that we were obtaining. So the second scenario, of course, that we considered was strain, and we basically considered different scenarios like uniaxial strain, biaxial strain, and so on. So the strain usually would give us rise to some sort of gapped-like looking feature, because the Fermi surfaces would not overlap perfectly with one another, and would, for certain momentum, would bypass each other close to small twist angles. And basically, this was basically giving us some sort of gapped structure. However, it would not give us these right splittings. And last but not least, we also considered next nearest neighbor hopping in the scenario, because it was also reported to give us some sort of nonlinearities in the past, but also this did not seem to match our findings. And what we sort of convinced ourselves is that really the findings are best fitted with this electron-electron renormalized scenario, which basically relies on the principle of reduced screening of the electrons close to charge neutrality point. And this scenario was actually introduced already some 15 years ago by Paco Guinea and others, who basically introduced the Fock term into the Hamiltonian, and they basically were basically looking at the electron-electron screening effects and the interactions with respect to sort of the screening. And the key idea here is really that at charge neutrality point, the electron population in graphene is so scarce that each electron really is separated by hundreds of nanometers, if not microns, and the electrons really do not screen each other efficiently. Therefore, at charge neutrality point, the Fermi velocity is actually enhanced. However, when you start filling up the the Fermi energy up in the band structure, more and more electrons get populated. They much more efficiently start screening one another, and therefore the Fermi velocity drops substantially. And this sort of transition basically gives something which these theorists have shown has a logarithmic correction to it. And this basically results in a slightly nonlinear band structure for the graphene. So this being said, this effect has been, of course, studied quite extensively. So some of the first sort of references to this correction came from the group of Andre Geim. Also here, Paco Guinea is the theorist on this work, where they basically looked at Shubnikov-de-Haas oscillation, and they were mapping out the Fermi velocity close to the charge neutrality point. Then also the group of Tala-Lazzara at Berkeley, they were seeing this effect through ARPAS measurements. And also the group of Joe Stroso in collaboration with Philip Kim, they saw this effect through STM tunneling experiments. And so basically the only surprising thing that was that we have seen this effect at elevated temperature, but in retrospect, it's not so surprising because actually the Berkeley group here also saw this effect already at 180 Kelvin. And really this sort of screening type of effect is really quite temperature insensitive, as we understood. So basically, it's kind of a natural explanation. So basically, here is some theory then introduced by Jonah in the Bernavik group. So we introduced this sort of nonlinear term into our calculations. And indeed, we get sort of this correct splitting type of behavior, as we see in our data, also at the right type of voltages, and also with the right type of sequence of splitting as we observe in our measurements. And so this being said, so of course, the main, I think, convincing point for us was that actually we were able to measure more than 20 devices with this sort of technique, so which showed all highly reproducible those features. And this to me is also a little bit the power of the QTM. So you could really just go and reproducibly map out many devices and get very quickly some sort of these phase diagrams that you wanna study. And this sort of cumulative phase diagram that we were able to obtain between the more, I mean, in this case, it's 9 devices that we put in this paper, but basically we were able to fit all of those 9 devices. We could basically extract the splitting features efficiently between 9 devices, and we could then perform the fit on this cumulative phase diagram with error bars on top of it. And so the Fermi velocities that we found here are well consistent with previous studies. So basically we find a Fermi velocity of 0.85, and we find an alpha, which is the fine structure constant in this correction term, to be in the order of 0.3, which again is in very good sort of agreement with previous studies, in particular with this STM data by Joe Stroso. So basically all this together really convinced us that these electron-electron interactions are present here. Okay, so basically I'm almost done. So I have 2 minutes, I just wanted to really highlight one last 2 slides before I end. And basically, I think what I wanted to also really mention is that, of course, in our field, we are always we're interested in fundamental physics, but we also often like to look for applications. And so one application that we've actually found for twisted biaxial graphene is in the area of quantum sensing, where we, in particular, we realized that really twisted biaxial graphene superconducting states can be very useful for single photon detection, and really cover a sort of field which area of single photon detection which is currently underdeveloped, in particular sensing of single photons in the terahertz domain. And so here really this principle of single photon detection relies on a very reduced thermal heat capacity of superconducting thin films. And this is a commercial technology for visible or near our wavelengths. where people basically cut out nanowires of superconductors, which are very, very narrow, in the orders of 100 nanometers and very thin, to basically reduce the heat capacity in such a strip. And the general idea is that when light is absorbed in such a narrow strip of a superconductor, it sort of can break the Cooper pairs, it can induce hotspots, and it can make the superconductor for a split second. It can make it normal and not superconducting, meaning that we can basically induce a voltage spike across the device that we can measure out. Okay, so but basically, in principle, what sort of the limiting factor of such detectors is how thin can you make the superconductor, how narrow can you pattern these strips, and how far you can reduce the heat capacity of the underlying substrate. And so basically here, for some years, we were already exploring 2D superconductors for this type of idea, because 2D superconductors are perfectly 2D, so they're just 0.3 or 0.6 nanometers thin. So they're an order of magnitude thinner than traditional spiral superconductors. And the other thing which is really nice about these superconductors is that they're all extremely low density. So because, as I mentioned yesterday, so twisted bilayer graphene has a carrier concentration which is extremely small. So here, per sheet carrier concentration is only 10 to the 11 of the superconducting state. And this is orders and orders of magnitude lower than in traditional superconductors, which are usually good metals. And so, long story short, we were over the years already using this type of graphene and 2D superconductors to perform some sort of gigahertz or mid-hour single photon detection capabilities. And of course, we also wanted to try this with twisted bilayer graphene. And so here is basically just the typical measurement scheme. So we actually just perform transport measurements on the devices to basically tune our IV characteristic close to the superconducting position. We shine a laser light on it, and we incorporate a negative electrofeedback loop, which allows us to reset the device when it sort of turns normal. And this is the last slide, is that indeed, so we were able to show that such a detector can actually really record clicks. And so the video that you see is sort of when we increase the laser power that we shine on the device. So we increase the number of photons that we shine on it. And as you can see, the density of these clicks increases. And in order to sort of convince yourself that those events have to do with really the single photons absorbing onto the surface, you have to basically perform some sort of statistical analysis. So you have to show that the Poissonian process, basically random absorption of these photons is given, which is shown sort of here on the left side. And you need to show that really the count rate is also the sort of the rate of the clicks that you observe is also proportional to the number of photons that you're sending on it. And if it's linear, so just what we observe here, then it's kind of a good argument that really the single photon clicking process here is really due to the single photons that you observe on the surface. So, okay, so right now we're also extending this measurement scheme to terahertz photons, where really currently no technology exists. And we have already had a theory paper that has already calculated that single photon detection, even in the terahertz, should be possible. Okay, so with this, I'm done, and I thank you for your attention. Happy to answer any questions.
Thank you for the nice talk. Yeah, so.
Hello, thank you for the interesting talk. I have one question about the quantum twisting microscope. So may I ask why it is necessary, or why there is a HBN layer inserted between the tip and the sample? Like, because from a theoretical perspective, I don't know the motivation.
Right. So basically, okay, so this was here, right? Okay, so basically, so of course, in principle, the QTM is very flexible, so you can build up your heterostructure for the type of purpose you want. So this particular measurement mode is really wants to explore the tunneling process, right? It wants to explore the energy conserving tunneling process between the tip and sample. And for this sort of energy conserving tunneling process, you want to have some sort of spacer, which basically allows your tunneling process. That being said, you could just also perform a conductance measurement where you would remove the HBN and you would just look at the conductance from the tip to the sample. This is also possible, but it does not give you this energy resolution. It would give you still some momentum resolution. It would not give you the energy resolution.
I see.
Mm-hmm.
Okay, thank you.
Yeah, so for your twisted bilayer graphene talk, where you say the superconductivity is near the some sort of insulating state, do you know actually any evidence for a role of magnetism in the case of cuprates and other sort of unconventional superconductor? It's well known that the magnetism always sort of plays an important role, right? Here, I mean, are there anything you can say about the mechanism or
Right. I mean, I think it's still under debate, right? It's not like a solved problem. All I can say is that, as you can see here, so it really is flanking this correlated insulator state, which again, as I mentioned before, STM groups have worked out, right, that it's likely an IVC or an IKS order, right? So basically. And if one looks at sort of the development of these gaps, they really develop somehow out of this correlated insulator gap. Right. So I think this is as much as I can say right now. Right. I mean, so I don't think we know the mechanism of superconductivity here, and we don't know the role of magnetism.
I see. I mean, can you say anything about whether it could potentially be BCS or?
Yeah. So basically, I think yesterday I had a slide on measurements of the superconducting order parameter symmetry, right? So basically, there are like a number of measurements that point towards a nodal superconducting gap. Those were measurements of STM, those are measurements of tunneling, and those are measurements such as kinetic inductance and superfluid weight, superfluid stiffness measurements. They all point towards a nodal superconducting gap.
Okay.
Right? But, yeah. But the verdict is still out there, I would say. The final verdict. But I think if you talk in the community, most people would sort of support a nodal scenario at this point.
Okay, we are actually running a little late, so one last.
Hi, Dmitri. Thank you. That was a great talk. I remember your work from a few years ago with Leonid Levetov that I that I read kind of naturally as a competition between the Fermi liquid regime and quantum critical regime.
Right.
Yeah. I asked yesterday about the T-squared behavior, and you said you would show it, and you really delivered. So thank you. Basically, my question is, given that that work, what is the coherence scale, like the T Fermi liquid temperature, and does it collapse when the strange metal begins? Because in heavy fermion, T-squared should emerge below some coherence temperature.
Right. Yeah.
How do we distinguish the disappearance of T-squared, coinciding with the vanishing Fermi liquid coherence instead of phonon crossover or something like that?
Right. So I mean, this is on point with what we're analyzing right now. So I hope to report something more concrete this year, actually. So we're really actively pushing this. So, but it's indeed so. What we showed, what we also seen already in the work of with Efetov, but now we think we have a better understanding of it. Is really that the transport coefficients. I mean, so basically, what we're doing right now, just to give you an idea. So, if you look at the bottom phase diagram here, you see there is a clear sort of separation between the t squared and the linear t regime, right?
Mm.
And actually, what you don't see here in this data is that really also the sort of the coefficients, these coefficients, right? AT, A1, and A2, they're also like kind of diverging close to this transition.
Right.
And so this is something which we're working out right now, and actually we're also happy to have discussions about this.
Okay, awesome.
So the data is there. The data is there. We're just now wrapping our head around it.
Awesome. Thank you so much. I have a super quick follow-up just on that sort of to the last point. This is kind of related to your more recent work with Andre. I'm just curious if this picture of the transport being controlled by the heavy carriers or the light carriers or their hybridization, because there's some argument in this thermoelectric paper with Bernevig, where
right.
This coexistence of these long-lived light carriers and short-lived heavier carriers near the integer fillings.
Right. So for that instance, this is also a work in progress, and also happy to hear comments. You see, so if you look at filling factor -2, you see a strong asymmetry between if you dope in the electron side or the hole side. And one of the most striking signatures is that the IVC order develops only on the hole side here, and also the superconductivity develops only on the hole side. And on the electron side, you basically get your Fermi liquid basically very quickly. So we're trying to wrap our head around it, looking at, in particular, at sort of again the predictions from the topological heavy fermion model, which is sort of which predicts these asymmetries right around filling factor -2. So basically, it would predict you that if you dope into this region here, you would get very quickly to the C electrons, whereas if you go into the other region, you would get into the heavy fermions very quickly. So so this is sort of what we're trying to work out right now.
Okay, awesome. Thank you so much.
Okay, let's thank the speaker.